Morning, guys. Today we're going to look at evaluating trigonometric expressions for angles that are not inside of, that won't fit inside a right triangle, non-acute angles. Now, if we step back to where we worked the other day, so we looked at sine of 60 degrees. We knew that when we saw sine of 60 degrees, we needed to build that special right triangle, that 30, 60, 90 triangle. So we would go through the process of building our triangle. 60 degrees, there's my right angle, and 30 degrees. And we remember that opposite of 30 was 1, opposite of 60 was the square root of 3, and the hypotenuse had a length of 2. Now, how that relates back to sine of 60 degrees was that sine was opposite over hypotenuse. So we knew sine of 60 degrees told us to take the opposite length, the square root of 3, and put it over the hypotenuse, the 2. Sine of 60 degrees is square root of 3 over 2. Worked with that before, so that was how we put that together. Now say we had something like sine of 120 degrees. Well, 120 degrees obviously does not fit into a 30, 60, 90 triangle or a 45, 45, 90 triangle. So then that comes back into what we worked with in the last section of angles in standard position. Now, if I took a 120 degree angle, I would draw that by putting my initial side on my positive x-axis. I would then rotate into quadrant 2 because 120 is between 90 and 180, and I get some quadrant 2 angle. That's a 120 degree angle. Well, this does not fit inside of a right triangle. So to get sine of this angle, because it all relates back to the right triangle, we have to use what we call as a reference angle. A reference angle, which I'm going to call theta prime in this example, is the acute angle between the terminal side of an angle and the x-axis. What all that means is if this is my terminal side, and say I had just dropped a point straight down to the x-axis. So the angle between the terminal side and the x-axis is going to give me my reference angle. Well, what's the reference angle for 120 degrees? What angle is between 120 and 180 degrees? We just subtract. It's the supplement, and that's going to be 60 degrees. So while 120 degrees does not fit inside of a right triangle, its reference angle, 60 degrees, does fit inside of a right triangle. And that's where we can find out what sine of 120 degrees is. Because we then tie this idea of reference angle into this relationship, which I used sine in this case, but it works for all trig ratios. The absolute value of sine of an angle is equal to the sine of that reference angle. So what in our scenario, absolute value of sine of 120 degrees would be equal to sine of 60 degrees. I can tell what sine of 60 degrees is. We know how to calculate that. It was square root of 3 over 2. 120 degrees, I didn't know the sine of, but what I do know now is the distance is the same. It's still going to be square root of 3 over 2. It's going to either be positive or negative, and we'll look at in a few minutes how to determine if it's positive square root of 3 over 2 or negative square root of 3 over 2. So anytime we see an angle that is greater than greater than 90 degrees. It won't fit inside of our right triangle. It's not one of our special angles for our special right triangles. We need to use this idea and find the reference angle and build one of those special right triangles off of it. Okay, guys, we're now going to look at how to calculate these using the reference angles. So sine of 120 degrees, if I draw it out, initial side, terminal side, get 120 degrees. And we know the reference angle was 60 degrees. So what that does for me is creates a quadrant 2, 30, 60, 90 triangle. 60 degrees, 30 degrees, right angle, 1, square root of 3, and 2. Now this 1 is not really a 1 anymore. It's now a negative 1. The reason it's a negative 1 is because we're having to go left 1 unit to be able to get to this terminal side. So left 1 unit and then up square root of 3 units. So that's where the absolute value that we talked about earlier came in. It's really the direction that your angle is pointing or your terminal side is pointing that's going to create the positive and negative trig ratios or trig values. So when we work this out, we remember that sine of an angle is equal to opposite, square root of 3, over hypotenuse, which is 2. So sine of 120 degrees does equal square root of 3 over 2. It was the same for sine of 120 and sine of 60. And we'll look in a minute about how those all relate together. And you'll start to develop a pattern for when is sine positive, when is sine negative. All right, now let's look at cosine of 225 degrees. So if I draw my angle in standard position, cosine of 225 degrees, initial side, 225 degrees should put me down here in quadrant 3 because it's between 180 and 180 and 270. So I've got some quadrant 3 angle of 225 degrees. But let's find the reference angle. The reference angle is between terminal side and the x-axis. Okay, so between 225 and 180 is going to be a 45-degree reference angle. So I've got this 45, 45, 90 triangle, and we just established the ratio of the sides. 1, 1, square root of 2. Except it's left 1, it's down 1, and hypotenuse is square root of 2. Now we know cosine of an angle is going to be adjacent over hypotenuse. So negative 1 over square root of 2. Go through, rationalize, times square root of 2, numerator and denominator. So cosine of 225 degrees equals negative square root of 2 over 2. Same ways we did it before with the 30, 60, or 45 degree angles. We're just now having to, we're going to change up those sides to be either positive or negative depending on what quadrant our terminal side is. And think about it. All the points on this terminal side should have negative x coordinates and negative y coordinates because we're going to go left and down to get to that terminal side. Let's say we have sine of pi over 6 sine of pi over 6. So if we draw the angle, pi over 6 would be a quadrant 1 angle. We looked at that yesterday when you were talking about converting from radians to degrees. So there's pi over 6. So we don't even have to find a reference angle in this case. Pi over 6 is the reference angle. Well, we're used to working with 30, 60, 90 triangles and 45, 45, 90 triangles. So pi over 6, if you remember from yesterday, is 180 degrees over 6, which is 30 degrees. Remember, pi is the same thing as 180 degrees. So it's going to be a 30-degree angle. So seeing sine of pi over 6, they're really asking you to find sine of 30 degrees. Just translate it back into what we're comfortable and what we know. Now, eventually, we'll have worked with these enough to where we see pi over 6, and we all automatically recognize 1, square root of 3, and 2. We start seeing it as a 30-degree angle, but for right now, just get in that habit of just transferring it from one form to the other, whatever you're more comfortable with. So sine of pi over 6, sine is always opposite over hypotenuse, so that's going to give us 1/2. Sine of pi over 6 is 1/2. Now, what about tangent of negative pi over 4? Well, where would negative pi over 4 be? And remember, negative means we're going to go clockwise from our initial side. So I'm going to go down pi over 4 units, or by pi over 4 radians. Well, if I'm going down, this was 0, 90, negative 90, negative 180, negative 270. Well, pi over 4 is a fourth of 180, so it was 45 degrees. So this is the same as tangent of negative 45 degrees. Negative 45 degrees would be a quadrant 4 angle. 45 degrees is going to be the reference angle in this case. And so we build a 45, so this is negative 45 degrees, but the reference angle from the terminal side back to the x-axis, there's 45 degrees in between. So we get a 45, 45, 90 triangle again, and it's going to be 1, 1, square root of 2. But this one has to be negative. Why does it have to be negative? Because we've got to go down to get to the terminal side. This one was still positive because we were going right to get to our terminal side, positive 1. Now we're going down, negative 1, to get to that terminal side. The hypotenuse is always going to be positive because hypotenuse is not really, when we're talking about these coordinates here, or these distances here, we're talking about the coordinates of this point on the terminal side. This is a distance from the origin to that point on the terminal side. So we don't put positive and negative on distances. We only need positive and negative when we're trying to express a direction with that distance, which we are here when we're putting the coordinates. This is the point 1, negative 1 on that terminal side. We'll talk about the points there in a minute or two. But back to tangent of negative 45 degrees. Remember, tangent was opposite over adjacent. So opposite of our 45-degree reference angle was negative 1. Adjacent was positive 1. So tangent of negative 45 degrees, or tangent of negative pi over 4 is negative 1. And all these can be checked on the calculator using the technique we looked at the other day. But we want to be able to do them by hand because we want these exact answers as we go through and check it. Now let's say we have cosine of pi over 2. Well, pi over 2, as you remember, half of pi, half of 180, was 90 degrees. So as I draw my angle, initial side, terminal side is 90 degrees. Well, 90 degrees fits within the 30, 60, 90 triangle or the 45, 45, 90 triangle, but it's not one of the sides, the angles that we can relate back to because everything was adjacent over opposite or opposite over adjacent or opposite over hypotenuse. Well, in a triangle, the opposite and the hypotenuse would be the same for the 90 degree. And it's got two legs that are adjacent to it. So we can't really use the same definitions as it relates back to that 90 degree angle. It only works for those acute angles. So we have to come up with another idea. Well, the other idea is similar to what I was just talking about with the points. If I look at a point on the terminal side, look at a point on the terminal side of this, we can, let's just pause on that for a minute. We'll come back to that in a moment. Let's say I have any angle. Any angle theta, and I've got a point xy on the terminal side of that. Now we want to be able to use our trig definitions, our trig ratios. Well, to do that, I need to be able to build a right triangle. So from this point, xy, I can build the right triangle that has a horizontal distance x, a vertical distance y, and then this distance from origin to the point, we'll call that r. And we call that r because we're kind of like we're rotating all the way around, so it's like the radius of the circle. Now, how that ties back in, well, once I've built this right triangle, I can use the idea of sine of theta is opposite over hypotenuse, is y over r. Cosine of theta is adjacent over hypotenuse, that's x over r. Tangent of theta is opposite over adjacent, y over x. And our trig ratios would all fit the same way off of that, or our inverse trig ratios that we had talked about before, reciprocal ratios. Cosecant would be r over y, cosine would be secant would be r over x, and cotangent would be x over y. So where I've got this idea of a point out in space or a point on the terminal side is now if I know the terminal side, then I can figure out, well, I can really figure out, work backwards and figure out what the angle is, but I don't really necessarily need to know the angle. So say I had this point negative 3, 2 on the terminal side. Negative 3, 2 on the terminal side. And I want to find out of theta. And I want to find sine of theta. Now, sine of theta is going to be opposite over hypotenuse. So we need to go back and identify what opposite and hypotenuse are. So if I draw my angle, or my point, negative 3, positive 2, that's the terminal side of theta. That's the terminal side of theta. Now we build this triangle. I went negative 3 units left, or went 3 units left, 2 units vertically. So I know sine, as we just described right there, is y over r. Well, my y is easy to see. It was up 2 units. My r, I'm going to have to calculate. Well, how do you calculate the hypotenuse of a right triangle? Well, we do that by taking r squared equals negative 3 squared plus 2 squared. A squared plus b squared equals c squared. So r squared equals 9 plus 4, which is 13. Take your square root, so r equals square root of 13. So we get 2 over square root of 13. So without even knowing an angle, just by knowing one point on the terminal side of that angle, I'm able to figure out what sine of that unknown angle is. In this case, it's 2 square root of 13 over 13. So I could use that for any time I'm given a point on a terminal side. Well, how does that help us with what we were working with a minute ago with cosine of pi over 2? Well, if we step back to cosine of pi over 2, I can say that I now know the terminal side. The terminal side has any number of points on it. So instead of looking at it as a reference angle situation where we had some point out here in space, since we have a quadrant angle, an angle between two quadrants, or a quadrantal angle, we can just pick any point on that terminal side. So just pick the point 0, 1. Easy enough. To get to this point, I just went over 0, up 1. So 0, 1, and I want cosine. Well, what was cosine? X over r. Horizontal distance over the radius of the circle associated with that rotation. So horizontal distance is 0, and the height, or the distance to that point, is going to be 1. R is 1 in this case, because from origin up to 1 is 1. So 0 over 1 equals 0. Cosine of pi over 2, or cosine of 90 degrees, is 0. That works for all quadrantal angles. Say that we had sine of 3 pi over 2. Well, 3 pi over 2, as you remember from yesterday, is going to be this 270 degrees here. 1 pi over 2, 2 pi over 2, 3 pi over 2. So again, we get an angle that's on an axis. It's a quadrantal angle. So we just pick a point on that terminal side. 0, negative 1, over 0, down 1. The r would be positive 1. So we've got our x, we've got our y. R is positive 1 because from the origin to this point is 1. Remember, your r is always going to be a positive value because it's a distance. It doesn't care about direction. The direction are picked up with the x's and the y's. So when I do sine, when I do vertical over the distance, y over r, my y is negative 1. My r is positive 1. So sine of 3 pi over 2 is negative 1. Now what if we did something like tangent? Let's do tangent We'll do the same angle, 3 pi over 2. Tangent of 3 pi over 2. So we draw it out. Initial side, terminal side, it's quadrantal angle, so let's just pick a point. On the terminal side, 0, -1. R is still 1. So for tangent of 3 pi over 2, tangent is opposite over adjacent, y over x. And tangent, realistically, we're just looking at it as like the slope right there. Y over x, so the y coordinate is -1. The x coordinate is 0. So -1 divided by 0 is undefined. So tangent of 3 pi over 2 at this point right here is undefined. And it is going to be very interesting to see how all these different values, different points start to put together, or how we start to piece them together to get the curves or the graphs of all these sine, cosine, tangent functions. And that's what we're going to look at in the next unit. That's really what we're working towards right now, to be able to do all these different calculations. So when you're working through these, if I've got an angle that is not acute, it's not a quadrant 1 angle, then what I've got to do is put it back into being having a reference angle that's one of those quadrant 1 angles. Okay, so if I can get the reference angle for a quadrant 1 angle, we just use the positive and negative to denote the direction of the side, and then we can just build it as we've been doing, the 30, 60, 90, or the 45, 45, 90. Now when I get a point on a terminal side where I don't know the angle, or when I get a quadrantal angle where I just have to pick a point on that side. When I get things that don't give me those special right triangles, then I'm going to use these relationships here for for sine, cosine, and tangent. And it's still off of the same definitions. Don't forget, sine is opposite over hypotenuse, x is adjacent over hypotenuse, and tangent is still opposite over adjacent. It's all built off of those 3 trig ratio definitions that we talked back in that first section on, and we're just expanding on it, putting these points out in space and moving outside of a confined right triangle. Okay. See y'all in class tomorrow.